Hi, Assalamualaikum everyone. In this video, I will explain to you on the topic of colloid and surface chemistry. These are the contents of this chapter. You may pause for a while to have a look at it. Okay, before I start, make sure that you have a note of chapter 7 with you. I suggest you to refer to this note by Madam Nura Amni. I will start with the definition of colloid. A colloid is a solution in which the substance remains dispersed and doesn't settle at the bottom. It consists of two components, which are dispersion medium and dispersion phase. Now we will learn the difference between a solution, suspension, and colloid. Aiman is having a glass of milk. Makdan is having a fresh orange juice. Meanwhile, Afam is having an iced tea. Milk, fresh orange juice, and iced tea are examples of mixtures. Milk is a colloid, orange juice is a suspension, and iced tea is a solution. What makes a colloid different from a suspension and solution? The particle size in colloid is intermediate between solution and suspension. Unlike solution, colloids do not form a clear mixture. We will now discuss the system characteristics of three types of mixtures. Mixtures are a combination of two or more substances or materials. There are three types of mixtures, which are solutions, colloids, and suspensions. Here is a diagram of mixtures. Mixtures are either form homogeneous mixture or heterogeneous mixture. Homogeneous mixture have the same uniform appearance and composition throughout. The types of mixtures under homogeneous mixture is solutions. Meanwhile, heterogeneous mixture have no uniform composition and appearance. The examples are colloid and suspension. Let us differentiate between solutions, colloid, and suspensions. Let's begin with particle size. The particles of a solution are smaller than colloids and suspensions. Among these mixtures, solutions have the smallest size of particles. It can be illustrated by the small circles inside the box. Now let us proceed to colloid. The particles of colloid are larger than solutions but smaller than suspensions. The particles are intermediate between solution and suspensions. The particles of suspension are larger compared to the solution and colloid. They have the largest particle size among these mixtures. It's just like a t-shirt. There are small, medium, and large sizes. Here in mixture, the small size is solutions, the medium size is colloid, and the large size is suspension. Now, let us move on to the appearance of these mixtures. Solution appeared clear and uniform, and which we cannot identify the components that we mix. For example, water with sugar. Colloids, on the other hand, appeared cloudy. We also cannot identify what we mix. For example, water and milk. Suspensions are as well appeared cloudy, but the components can be recognized. For example, water with oil. Here, in this example, all components settle on the top of water. Now let us talk about filterability or ability of being separated by filtering. Solution cannot be separated by filtration. The particles are smaller than the pores of the filter paper and they can pass through it. Same as colloid, it cannot be separated by filtration. In suspensions, the components can be separated by filtration. For instance, oil can be separated from water by filtration. The particles of oil are larger than the pores of the filter paper, and so it cannot pass through it. They will remain on the top of filter paper. The last characteristic is Tyndall effect. Tyndall effect is the scattering of visible light by particles in a colloid or in a very fine suspension. It is only visible when there are large particles like dust or mist which can scatter the light. In solution, Tyndall effect cannot be seen. The particles are too small to scatter the light. There's an experiment on Tyndall effect in solution. This is a solution of water and vinegar. As you can see, no path of light can be seen in the solution. In colloid, Tyndall effect can be seen. This is a mixture of water and milk. Tyndall effect can be observed in colloid since the particles are large enough to scatter light. The light can penetrate this mixture. Tyndall effect in suspension can be seen. This is a mixture of water and oil. This example of suspension exhibits Tyndall effect on part of concentration of oil above the water. The examples of solution which do not exhibit Tyndall effect are vinegar, alcohol, and soda. The example of colloid in which Tyndall effect can be seen are paint, mist, and gelatin. The example of suspension which Tyndall effect can also be seen are flour in water, muddy water, and peanut butter. To sum up, the particles of solution are the smallest, the particles of colloid are intermediate between solutions and suspensions, the particles of suspension are the largest among these mixtures. Solution appear uniform, colloid and suspension appear cloudy. Solutions and colloid cannot be separated by filtration, while suspension can be separated by filtration. Solutions do not exhibit Tyndall effect, while colloid and suspension exhibit Tyndall effect. Colloids can be classified into different groups. This includes gel, sol, foam, emulsion, and aerosol. Earlier, we have discussed that colloids contain dispersed phase, which is the particulate components, and dispersion medium, which is the substance that the particulate disperse in. The dispersed phase and dispersion medium can each be of any different phase. Smoke is solid dispersed in gas. Clouds, fogs, and mist involve liquid dispersed in gas. Milk, mayonnaise, and butter involve liquid dispersed in liquid. Jelly and gels are liquid dispersed in solid. Foam and whipped cream involve gas dispersed in liquid. Now we will go into details of each type of colloid. Sol is a dispersed system, which the dispersed particles is solid and the dispersion medium is liquid. There are two types of sol. The first one is Lyophilic sol, which is solvent loving, and the second one is lyophobic sol, which is solvent hating. It's easy to remember which one is which. Lyophobic, the word phobic means fear of something, so remember lyophobic is solvent hating. Therefore, lyophilic is the other way around. In the case of where the dispersion medium is water or aqueous, a different term will be used. Lyophilic sol is changed into hydrophilic colloids, which is water-loving. By definition, hydro is water, so if the dispersion medium is water, it is called hydrophilic colloid. Now we will learn how to differentiate between lyophilic and lyophobic colloids. Lyophilic colloids pass into the colloidal form readily when brought in contact with solvent. Meanwhile, lyophobic colloids do not form the colloidal solutions easily when treated with solvent. They are called the reversible sols because they can be recovered from the colloidal solutions and can be converted into the colloidal form when desired. They are called irreversible sols because they cannot be recovered from the colloidal form. Small quantities of electrolyte do not affect the precipitation, but only large quantities of electrolytes can cause precipitation. Even small quantities of electrolyte can cause precipitation. The particles are not easily detected in the ultramicroscope. The particles are easily detected by an ultramicroscope. The particles may or may not migrate an electric field. The migration may be in any direction. Particles migrate only in one direction. Substances like starch, proteins, gums, soaps, and metaxylic acid are common. Colloids of metal, such as gold, platinum, sulfur, Arsenious, sulfide, and silver iodide are common examples. Gel is a semi-solid form of a lyophilic salt in which the dispersion medium has been absorbed by the salt particle. It appears like a solid but easily deformed. Gel retains its characteristic shape. The uses are jelly candies, toothpaste gel, gel soap, and etc. When oil and water are added together, they form two distinct layers. This is because they are immiscible to one another. In other words, they do not mix. Even if you shake the two liquids vigorously, they will remain immiscible. Let us look closely at what we have right now. There are tiny oil droplets are dispersed throughout the water. We have just created an emulsion. What do you think will happen if we let this emulsion stand for 5 to 10 minutes? Since oil and water are immiscible, the oil droplets will reform original layer. Common everyday emulsions include milk, mayonnaise, ice cream, and paint. These emulsions are mostly oil droplets in water. Emulsion can also exist as water droplets in oil. Real-life examples include margarine, lotion, and facial creams. The world's most popular emulsion is ice cream. The main ingredients are milk or cream, a lot of sugar, with flavoring or coloring components. So what prevents an emulsion such as ice cream from separating? Substances as emulsifiers are added to stabilize emulsion. When making ice cream, egg yolk is commonly added. The active emulsifier in egg yolk is lecithin. Too little lecithin will cause the ice cream to separate, and too much will ruin its texture and flavor. All emulsifiers have two components, a hydrophilic part, which is water-loving head, and a hydrophobic part, or water-fearing tail. If we add lecithin to our original oil and water emulsion, its hydrophilic head will prefer to associate with water, and the hydrophobic tail with the oil droplet. This prevents separation and thus stabilizing the emulsion. In summary, emulsion is a mixture of two substances that is immiscible with one another. This emulsion can be stabilized by adding emulsifiers. There are two types of emulsions. The first one is oil in water emulsion, and the second one is water in oil emulsions. For the first type, oil in water emulsions, in this case, oil acts as the dispersed phase, in which it is in a small amount, and water as the dispersion medium in excess. Example is milk in an emulsion of soluble fats in water. Such type of emulsions are called aqueous emulsion. As you can see in the picture, the dispersed phase is oil, the oil droplets, and the dispersion medium is water. Next, the second type of emulsion, water in oil emulsion. In this case, water acts as a dispersed phase, while oil behaves as a dispersion medium. Examples are butter and cold cream. Such type of emulsion are called oily emulsion. As you can see in the picture, the dispersed phase is water. Meanwhile, the dispersion medium is oil, so it is droplets of water in oil. These are the methods of preparation of colloidal solution. There are three methods. The first one is dispersion method. Under dispersion methods, there are three techniques. The first one is mechanical dispersion. Second is baptization. The third one is Briggs out method. Meanwhile, the second method is condensation method, and the technique is exchange of solvent. Meanwhile, the last is chemical methods. There are four techniques under chemical methods. The first one is hydrolysis, second is redox reaction, third is double displacement, and the last one is reduction. Okay, the first technique in dispersion medium, which is mechanical dispersion, the substance to be dispersed is suspended in the dispersion medium and then ground to final state by mechanical means. The bigger size particles, which is the suspension, change into smaller size colloids. grinding machine or colloid mill used in industry. This machine is equipped with metal plates spinning at high resolution and in opposite direction. Solid powder, which is the dispersed substance, and liquid are mixed in the machine. Colloid particles are produced and dispersed in the dispersing medium. This method can be used to produce graphite colloid, which is lubricant, and printing ink. The second technique is preparation of colloids by baptization. Baptization is the process of converting a precipitate into colloidal form by shaking it with dispersion medium in the presence of small amount of electrolyte. The electrolyte used for this purpose is called baptizing agent. During baptization, the precipitate absorbs one of the ions of the electrolyte on its surface. The absorbed ion is generally common with those of the precipitate. This causes the development of positive or negative charge on the precipitate, which ultimately break up into smaller particles having the dimension of colloids. The last technique under dispersion method is Brady's arc method or electrodispersion method. The method employed for preparing the colloidal salt of gold, silver, and platinum. Two rods drawn out of the metal are dipped in the conductivity water to which a small quantity of alkali hydroxides has been added and an electric struck between them. Arc heat would vaporize some of the gold electrodes, and the gold vapor then disperse into the alkaline medium to form salt. The vessel containing the water may be surrounded by a freezing mixture if necessary. The addition of alkali to the conductivity water helps to get more stable colloidal solution, which can be freed from particles of non-colloidal size by filtration. Now we will move on to the second method, which is the condensation method. The technique under condensation method is extraction of solvent. There are certain substances which are more soluble in one solvent as compared to another. Colloidal solution of such substance can be obtained by pouring the solution of the substance from more soluble to the less soluble solvent. The first example is sulfur and phosphorus are more soluble in alcohol than in water. If the alcoholic solution is added to a small quantity of water, hydrosol is formed. The second is phenolphthalein is soluble in alcohol but not in water. If the alcoholic solution is added to water, milky solution is obtained, which is a salt of phenolphthalein. Next is chemical method using hydrolysis. Colloidal form when the substance is react with water. Hydrolysis is the preparation of oxides or hydroxide salt. The preparation of lyophobic solution aim to prepare lyophobic solution of ferric hydroxide. First, measure 100 ml of water and heat it to 80 degrees Celsius. Now you can see the water starts to boil. Add 30% of ferric chloride solution drop by drop. Continue heating and adding ferric chloride solution until deep red or brown color appears. Here you can see that the appearance of brown color solution. We have successfully prepared lyophobic ferric hydroxide solution. Okay, now we proceed to redox reaction. Oxidizing agent is needed in this reaction. The example are bromine water, nitric acid, and sulfur dioxide. In this experiment, we are going to prepare colloidal sulfur or sulfur salt. Please refer to the chemical equation in the lecture notes under redox reaction. As you can see, in the product, we are going to form a sulfur salt which is yellow in color. First, we add hydrogen sulfide into sulfur dioxide. These two will undergo oxidation process to form water and sulfur salt. This is how we are going to prepare colloidal sulfur or sulfur salt. So now we will move on to the next method, which is double displacement method. We will look at the chemical reaction of silver nitrate plus sodium chloride. Please refer to the chemical equation provided in the lecture notes. Silver nitrate is AgNO3 and sodium chloride is NaCl. In this equation, Aq means aqueous, which is dissolved in water. And the S after the silver chloride is solid or salt. Here we are adding NaCl to the water, that means it breaking apart into ion. We get Na plus and Cl minus from the NaCl. They are aqueous and they dissolve in water. We also have AgNO3. We put water in it, we get Ag plus and NO3 minus. It dissociate or dissolve. Now that we have these two aqueous solution, AgNO3 and NaCl. We will mix them together. Remember that they are both aqueous, so they split apart into their ion. This is what happens. The AgNO3 and NaCl are changing their places using double displacement reaction, and we get AgCl, which is a solid or salt. A precipitate is a solid and falls to the bottom of the beaker. What's left in the beaker is sodium ion and nitric ion, and the chemical reaction took place there. The chemical reaction will look like this: AgNO3 plus NaCl. They are both dissolved in water and react to form AgCl, solid or salt, which is the precipitate, and NaNO3 aqueous. In this experiment, we have formed a salt, which is AgCl. The last technique in chemical methods is reduction. In this reaction, we are going to involve reducing agent. Now we are going to prepare silver salt. First, ammonia solution is added to 5 cm³ of silver nitrate 1% solution. The mixture is shaken until all Ag2O solid is dissolved again. Dilute the mixture in 95 cm³ of water or H2O. Add 0.5 cm³ of tannin solution. The function of tannin is to give some color, and Ag salt, light brown in color, is produced. Gold electrodes immerse in the dispersing medium. Now we will go into the properties of colloid. There are 5 properties. We will go into the first one, which is optical properties. Light scattering and Tyndall effect. When an intense converging beam of light is passed through a colloidal solution kept in a dark, the path of the beam gets illuminated with a bluish light. This phenomenon is called Tyndall effect, and the illuminated path is known as Tyndall cone. Dimensions of colloidal particles are comparable to the length of ultraviolet and visible radiation. They scatter these and get illuminated. An intense beam of light is focused on the colloidal solution contained in a glass vessel. The focus of the light is then observed with a microscope at right angle to the beam. Individual colloidal particles appear as bright stars against a dark background. Tyndall effect is not exhibited by true solutions. This is because the particles, ion or molecules present in a true solution are too small to scatter light. Tyndall effect can be used to distinguish a colloidal solution from a true solution. The phenomenon has also been used to devise an instrument known as ultramicroscope. Tyndall effect is observed only when the two conditions are satisfied. The first one is the diameter of the dispersed particles is not much smaller than the wavelength of the light used, and the refractive index of the dispersed phase and the dispersion medium differ greatly in magnitude. The second property is Brownian movement. The constant rapid zigzag movement in colloids is caused by the unequal bombardment of colloidal particles by the molecules of the dispersed medium. The higher the temperature, the more vigorous is the movement of the molecules. Electrophoresis is the movement of charged particles through a liquid under the influence of electrical potential. Due to the presence of a particular type of electrical charge, the colloidal particles present in a colloidal dispersion move towards a particular electrode under the influence of an electric field. The direction of movement of the colloidal particles is decided by the nature of the charge present on them. If the colloidal particles carry positive charge, they will move towards the negative terminal. Meanwhile, if the colloidal particles carry negative charge, they will move towards the positive terminal. A colloidal solution as a whole is electrically neutral in nature. For example, dispersion medium carries an equal and opposite charge to that of particles of the dispersed phase. When the movement of dispersed phase of colloidal solution is prevented by suitable means, the dispersion medium can be made to move under the influence of an applied electric field of potential. This phenomenon is referred to as electro-osmosis. Thus, electro-osmosis may be defined as the movement of the dispersed medium under the influence of an electric field. If the dispersed phase molecule has positive charge, they will move toward cathode, and if the negative charge, they move towards anode. The next property is coagulation of colloids. The precipitation of a colloid through induced aggregation by the addition of some suitable electrolyte is called coagulation. The coagulation of a colloidal solution by an electrolyte does not take place until the added electrolyte has the certain minimum concentration in the solution. The minimum concentration of the electrolyte in millimoles that must be added to 1 liter of the sole so as to bring about complete coagulation is called coagulation value of the electrolyte for the sole. Different electrolytes have different coagulation values. Smaller the coagulation value of the electrolyte, larger its coagulating power. The next property is dialysis, the process used for reducing the amount of impurities to a requisite minimum is known as purification of colloidal solution. Dialysis is a process of removing a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. The apparatus used for this purpose is called dialyzer. We also have an electrodialysis. The process of dialysis is quite slow. It can be faster by applying an electric field if the dissolved substance in the impure colloidal solution is only an electrolyte. The process is known as electrodialysis. From these pores, small impurities and electrolyte get diffused from the solution, but large colloidal particles remain within the solution.